Force will be with you, always.
Okay, we are live, kind of. We're not live on Mixer. I should remove that command. But yeah, so hello. You can call me KD. We see each other for the first time, or at least you see me today for the first time. And today I want to talk about a little bit about limits. I know I gave you a lot of reading to do this past week, but fundamentally, only 2 sections out of that reading matter in the long run. If you're studying for the AP, maybe you want to pay attention to the section in which you compute limits by hand using a table without using any of the actual limit laws and any of the actually rigorous definitions. But today we really want to talk about Stewart 2.4 and 2.5. 2.4 being a rigorous definition of continuity, rigorous definition of limits, and 2.5 being definition of continuity. And the reason I fast-tracked you so quickly through chapter 1 and then to the first few sections of chapter 2 is because those chapters are just building up intuition for 2.4 and 2.5. So if you haven't caught up on the reading, if you're just still stuck on chapter 1, fast track through that, see how far you can get through 2.4 and 2.5, and if you don't get something, then maybe just go back and read chapter 1, read chapter 2. Before I proceed with my instruction, I will post the quiz and the homework tonight after we do this short talk. If for some reason you're not here for Calculus 1, but for linear algebra, I will continue with linear algebra at 9:30. Again, I know there's a lot of demand for that too. My own students in my own university have an exam tomorrow, so they're very anxious and they might have turned up a little bit early. But now we'll talk about calculus. Feel free to stay here if you are interested in learning about calculus. So let's start with a little bit of like what happened in 2.4 and what 2.4 tells you. And you have the following fundamental definition, and I will just write the definition and then I'll explain how it makes sense in the context of 2.3, 2.2, 2.1. So let's talk about 2.4, definition of a limit. And before you tell me my handwriting is awful, I know, but it's the best we got. I cannot late take real time, unfortunately. Okay. So let's give the rigorous definition of a limit definition. We say lim x arrow to a, f of x equals to L if for every epsilon greater than 0, we can find a delta greater than 0 such that, colon usually in math means such as, or such that, if x minus a is less than delta, then f of x minus L is less than epsilon. So this is the formal definition. You can look this up in your textbook. Literally every single calculus textbook ever will give this definition. And usually this definition on the first exam in Calculus 1 is the hardest thing to try to get to. Students are really good at computing derivatives. Usually students are really good at computing a lot of stuff, but they're really struggling usually with the definition of a limit. And that's what we'll spend about 20 minutes on today. Then we'll talk about 5 minutes on continuity, and then I will answer any questions you have. And then once we answer those questions, then we'll just disperse. But for now, let's try to unpack what this definition means. And it has 2 parts. So it tells us that if we fix an epsilon, then we can find a certain number delta that corresponds to epsilon. Now, delta can be thought of as a function of epsilon, And one thing that's important to realize is that as I am not live on Mixer, shut up Nightbot, I should disable that. One thing to keep track of is that as epsilon gets smaller and smaller, your delta will also get smaller and smaller, usually. So let's understand what's going on here. What this definition is telling us is that the limit of a function is L as your argument. So this is what we usually call the argument. As the arguments get closer and closer to A, the function gets closer and closer to L. And this is the definition that, or this is the intuition that section 2.3 in Stewart was trying to teach you. And if you're not sure what Stewart I'm referring to, again, exclamation point book in chat should give you what Stewart we're referring to. In the normal Stewart and just the Stewart calculus, it might be a little bit different. Yes, as you approach the X, you approach the Y basically, is the correct intuition. But the main takeaway from what we all just said here is the closer you get to A, the closer the function is to L. And let me just turn on an extra light. Okay, so this is our definition. We're gonna take a screenshot of it so we can come back to it in a bit. And we will move on. And we will look at how we can actually apply this definition to prove some basic stuff about limits. Stuff that is so basic that you usually just take for granted because you don't want to prove it over and over again. So we're gonna have the following basic theorem. The limit as x goes to A of f of x, let's start this over again. Limit x goes to A of x equals to A. Yes, so we will show how we actually prove that basic limits are as they are. And we'll only prove the basic stuff because this is calculus 1. It's not a rigorous math class. But these are the types of problems you would usually see on university level exams, like something like this. So prove that. Well, let's start with the proof. And every proof about a limit always starts with the following 3 words, or 4 words, 5 words, 5 words. Fix epsilon greater than 0. Right? So if we flip all the way back to this, we have to show that for every epsilon we can find a delta such that this relationship holds. Right? So every proof about limits ever starts with fix epsilon greater than 0. Right? And one of the lamest math jokes is, and I hope you listen to this carefully because it's very short, take epsilon less than 0. And that's a joke because you always fix epsilon to be greater than 0. Okay, if you're laughing, if you're on the floor, I'll wait for you to come back up so we can continue. Fix your epsilon. Well, now we have to find the delta. Delta greater than 0 such that if x minus a is less than delta, right, and this is the x that comes from here, this is the argument x, then x minus a is less than epsilon, and this is the function. And for a lot of these problems, what you will usually have to do is understand the difference between argument x, or argument k, or argument t, or whatever the argument is called, and the function expressed in terms of that argument. And we will do one more example in a bit just to solidify this. But now understand, this is the argument x. Here we're getting closer and closer to the argument. argument. My handwriting is going out the window. And here we're getting closer and closer in the sense of the function. And now we are reaching the student's favorite part, which is guessing. Or in other words, just pulling a delta out of thin air and showing that it has the required properties. A lot of math is like that, unfortunately. Or fortunately, because it's a very creative discipline. So what we're going to do here is we're going to put a delta out of thin air, and we're going to show that for the fixed epsilon, that delta works. Okay, are you still with me? I hope you're still with me. Let's see how this one is going to work out. So take delta equals to epsilon. In other words, as we said before, delta is supposed to depend on epsilon, and as epsilon is getting closer and closer to 0, delta should also be getting closer and closer to 0. Well, in this case, let's look, as epsilon is getting closer and closer to 0, delta is getting closer and closer to 0, and delta depends on epsilon. We've satisfied our two initial ideas about what delta should look like. Okay. Now, let's finish the problem. So, suppose x minus a is less than delta, which equals to epsilon, then clearly x minus a is less than epsilon. Right, and this seems like a gigantic tautology, but we just proved that for every a, the limit as x goes to a of the function x equals to a. How? We use the epsilon delta definition of the limit, the rigorous definition of the limit. We fixed our epsilon greater than 0. We said we have to find a delta. First, I don't know what you were trying to spam, but don't spam it. So we fixed our epsilon greater than 0. We said we have to find a delta with those properties. And then as we educatedly guessed, delta equals to epsilon would work. I will just type the ask for you. I am not sure why it would time you out. But yeah. So let's take a breather here. Let's try to understand how this basic proof went, and then we're going to do another one. We're going to do another one with another function of x that is very, very common. And then if you have any questions, if you read something in the book that you need me to clarify on 2.4 and then later in a bit in 2.5, then we can do that. For now, I'll take a screenshot. We will do a big recap at the end, but for now, let's just flip the board back up and try to prove another one. And in a bit I'll have to clean the board again, but for now we'll just leave it a little bit smudged. Okay, so now let's do another proof. So theorem, limit x goes to a of x squared equals to a squared. Okay, there is some logic to the madness here. As we're just taking powers of x, and we're proving it now for x squared. Well, let's check it out. We're not going to use the limit laws because we haven't talked about the limit laws yet, but we will talk about how we would just prove this using epsilon delta. Okay, so proof. Well, what's going on here? As usual, fix epsilon greater than 0. Right? We fixed epsilon greater than 0. And now we want to find delta. Delta greater than 0 such that if x minus a is less than delta, x squared minus a squared is less than epsilon. Again, this is the argument part. And this, well, is the function. It is first, if you're asking about this particular board, it should be a times a. Should be x goes to a in the limit, and then x squared equals to the limit of x squared equals to a squared. So what are we looking at? We are looking at this, and we have to somehow guess a delta. Well, let's just chill for a bit, right? Let's try to come up with something interesting here. And let's look at this part. In this part, we see something very familiar. So let's look at this. X squared minus a squared. Something I didn't talk about enough is these absolute values. And these absolute values are a lifesaver. Why? Because they measure distance. And the absolute value of, say, a negative number, say -2 equals to the absolute value of a positive number of the same size. So absolute value of -2 equals to absolute value of 2. And we use these absolute values to quantify what we were saying before, which is the closer you get to something, the closer you get to something else. Closer in this case means distance, which is why we use these absolute values. Okay. So now let's factor this, but we can't factor it just yet completely, so we'll just keep it in the absolute values. Well, x squared minus a squared is x minus a times x plus a. Right? Well, now we're just going to make a small box here to say that absolute value of a times b equals to absolute value of a times absolute value of b. And this is just a theorem. And this is something that you can very straightforwardly just observe. If you say take -2 and 3, -2 times 3 is -6. Absolute value of 2 times absolute value of -2 times absolute value of 3 is 6, which is the absolute value of -6. So we can also now use this to factor x minus a times x plus a inside the absolute value to say that this is x minus a times x plus a. So we've factored the function difference here as an x minus a and x plus a. But now x minus a, we already know something about that, right? We already know that x minus a is maybe less than delta once we fix our delta. Okay. So now the idea here is to take delta, such as delta times x minus a, or x plus a, excuse me. So this becomes delta, this becomes x plus a in absolute value. Delta times x plus a in absolute value is less than epsilon for x minus a, for the x's, let's write this in words, for x such that x minus a is less than delta. So if x is very close to a, we want to find such a delta that it would be possible for delta times x plus a to be less than epsilon. Okay. Let's try to digest this. We would be looking for such a delta, but how would we actually find it? Well, let's keep working. So we will take a screenshot and we'll actually do the recap after this problem is done. Let's just take the screenshot, flip the board and continue working, and I'll just copy this last line over again. And by the way, if you somehow stumble upon this and you're a new viewer, not in my Discord, I will post the links to my Discord very soon, in case you want to join and look at what we're working on. I am looking for motivated students to just help in calculus. I am doing this absolutely pro bono. I do not care about fortune or fame or money. I just want to teach people calculus. But let's keep going about this. So we want to find delta greater than 0 such that delta times x plus a is less than epsilon for all x such that x minus a is less than delta. Okay. So far so good. And it's an a. Okay. So now we're going to try to be very, very, very smart. Remember, a is fixed. A is And in particular, we're allowed to let delta depend on A. We're allowed to let delta depend on A. We're allowed to let delta depend on epsilon. And that's what we will try to do. Now, there is this thing called the triangle inequality. The triangle inequality goes like the following. And it's again an inequality about absolute values, just like the inequality we wrote on this side of the board. Just like this thing we wrote over here. We need to know a little bit more about absolute values and distances. So A plus B in absolute value is always less or equal to than the absolute value of A plus the absolute value of B. I'm sure at least a few of you have seen this before. Just make sure that you internalize it, because this inequality is used all the time in the statements about epsilon-delta proofs. And if you're studying for the AP, maybe you don't encounter enough epsilon-delta proofs, but maybe just this one time they decide to give it to you. I would have to check whether that's in the syllabus, but I would imagine they have at least a little bit about it, especially probably on the BC part. Okay, so how are we going to weaponize the triangle inequality here? Well, x plus a and x minus a look awfully much alike. They're one sign apart. Well, let's see how we're going to fix this. Well, let's write x plus a as x minus a plus 2a. Well, now we can apply the triangle inequality to these two parts. X minus a plus absolute value 2a. Okay. Well, now suppose x minus a in absolute value is less than delta, and delta is in turn less than absolute value of a, or less or equal to than absolute value of a. Well, then x plus a is less or equal to than x minus a absolute value plus 2a absolute value, and you can factor out the 2. And then this becomes strictly less than 3 times absolute value of a. Okay. And now for delta times x plus a to be less than epsilon, it suffices to find the delta such that delta times 3 times absolute value of a is less than epsilon. So what did we do here? We said, without fixing delta, just suppose for a second it was less than the absolute value of a. And there's something small that we would have to fix here, and we will fix it in a second. But given that 99% of your problems in practice will be solvable by this, you can just apply it this way. Suppose that the absolute value of delta was less than or equal to than the absolute value of a. Well, then you would just have to find a delta such that delta times 3a is less than epsilon. Well, you just pick delta less than epsilon over 3 times. Okay, so we want our delta to be less or equal to than absolute value of a, and we want our delta to be less than epsilon over 3a. We have a very nice function that would give us such a delta, and I will write that here so we're on the same page. Pick delta equals to the minimum of absolute value of a and epsilon over 3 times absolute value. And that delta we have already demonstrated works, and we're done. Or at least we're done in 99% of our problems, because usually your problem is going to have the following statement, gonna give you a specific A. Going to give you the exact A that you're looking for. Right? It's not going to give you a general A, it's not going to be a proof of this type. Right? It's not going to be a proof of this generalistic type, proof that this is true for every A. Instead, what will usually happen is that you will be given a problem in which your a will be fixed, and your a will usually not be 0. Our thing, unfortunately, breaks for a equals to 0. So let's just quickly fix it for a equals to 0. So let's take a screenshot. We're almost at the point at which we'll be able to recap. Okay, so what if a is equal to 0? Well, let's look at it again. So fix epsilon greater than 0 and find delta such that delta greater than 0 such that if x minus 0 is less than epsilon, less than delta, excuse me, then x squared minus 0 is less than epsilon. Wow, very, very obviously. We can just take delta equals to square root of epsilon. Be done. So, what is our answer for delta? Delta equals to either square root of epsilon if a equals to 0, or the minimum of, let's just cheat and look back because I don't remember, the minimum of absolute value of a and epsilon over 3 times absolute value of a. And that's your answer for how you find delta, and that concludes your proof. Okay. Now let's solve a practical question like that. So, hello, noob Vincent. If you're here for calculus, then you're at the right time and the right place. If you're here for linear algebra, you're 3 hours early, because we're doing calculus right now. So let's just take a quick screenshot and try to recap what we just did, and I'll just need a second to set the recap up. Or maybe not. Let's see. Maybe I can just rotate this. No, I just need a second to set the recap up. Okay. Okay, so this is the definition we gave earlier. We are saying that if x minus a is close to 0, then f of x minus a would be close to 0 as well. Then we proved that the limit of x is equal to a, and that was straightforward. You just pick delta equals to epsilon. The not so straightforward part is the next part, which is prove that for every a and for every a possible, then the limit of x goes to a, x squared equals to a squared. What we did here was try to very carefully understand what a good educated decision about the delta would be. And to see how we would do that, we just slowly worked through the factoring of x squared minus a squared. Right? And the idea here was to try to find a delta such that if x minus a was less than delta, then delta times x plus a would be less than epsilon. Now, you could technically try to solve this as a quadratic inequality, but we hate that because it's clunky, you get it wrong a lot of the time. Instead, we're going to cheat, and we're going to use this minimum function you see in the top right corner. Top right corner, yeah. If you use the minimum function, then you can impose different restrictions on your delta that help you prove the inequality that you're desiring. So by using the triangle inequality, we saw that if a was not 0, then it sufficed to pick delta less than or equal to absolute value of a, and then also delta less than epsilon over 3 times absolute value of a. And how we worked through that, you can check it again in the VOD if you missed some of the words, or you can just look at it on the page right now. We used the triangle inequality, and we said, if delta is less than absolute value of a, then x plus a was less than 3 times absolute value of And because of that, then you just plug in x plus a equals to 3 times absolute value of a in your previous inequality, and you get that it would suffice for delta to be less than epsilon over 3 times a. Take a breather. Just look at the page. Remember, you can always go back to the VOD. If you're trying to take notes immediately as I'm speaking, you're going to lose on a lot of the value of hearing this live right now. Again, listen, don't write anything yet. Finally, we had to fix something about x a equals to 0, just so our solution was complete. And for a equals to 0, it would have just sufficed to pick delta equals to root epsilon. So the final solution was if delta equals to root, if a equals to 0, then delta equals to root epsilon. Or if a was not 0, then just take the minimum of absolute value of a and epsilon over 3 times absolute value of a. And we are happy. We can play a short but sweet. Let me see if I can find my music clip. I can I? It kind of already ruined itself. Nope, my music clip is not here. Whatever, I have a very nice music clip I like to play when we're done with the problem. So this is how you approach these questions for a general A. Now let's see how we would approach it for a specific A. Let's see how we would solve a similar question, an actual question that you could maybe see on an actual exam at the level at which we are learning this. Let's try to solve the following question. Prove or show that limit of x cubed as x goes to 2 equals to 8. So, solution, x epsilon greater than 0. We want to find delta greater than 0 such that if x minus 2 is less than delta, then x cubed minus 8 is less than epsilon. Right? Same thing. The first two lines of this solution are always going to be the same. After the first two lines, then we have to do something else. Right? We have to apply our gray matter and try to come up with what actually is going to be going on here. Okay. So now, as with the x squared part, hopefully you can recognize that x cubed minus 8 is indeed a difference of cubes. And if you don't remember how to factor differences of cubes, now is a good time to review that. X cubed minus 2 cubed equals to x minus 2 times x squared plus 2x plus 4. Okay? Well, again, we're going to split this up into two absolute values, x minus 2 and then x squared plus 2x plus 4. Okay. And now we have to apply something clever. We're going to be very, very, very smart about this. Okay, so now let's look at just this part. Right, so we want to have, so if x minus a was less than delta, we want to find some nice bound on x squared plus 2x plus 4 in absolute value. Okay, and because it doesn't really matter, I'm sorry I bumped my mic, it doesn't really matter how big delta could be. Like, we don't care about big deltas, we care about small deltas. I would say suppose, and this is not an A, this is a 2. So if x minus 2 was less than delta, then we want to find a good bound for this. Well, suppose that x minus 2 was less than 1. In other words, delta less or equal to 1. Well, then x squared plus 2x plus 4 using the triangle inequality multiple times, you get that this is less than the absolute value of x squared plus 2 times the absolute value of x plus 4. This is by the triangle inequality. Okay. Well, let's keep going. What smart thing can we say after we take a screenshot? You can say the following really smart thing, which is that since x minus 2 is less than 1 in absolute value, then x is less than 3 in absolute value. So I don't need to write in absolute. Absolute value of x is less than 3. Why? Again, by the triangle inequality. X plus negative 2 in absolute value is less or equal to then absolute value of x plus absolute value of negative 2. I'm doing the triangle inequality wrong here. So let's do it a different way. So what does it mean for x minus 2 to be less than 1? Well, x minus 2 is between 1 and negative 1. That's what it means for your absolute value to be less than 1. Well, just add 2 to both sides. X is between 3 and 1. And the absolute value of every number between 3 and 1 is less than 3. That's why this is 2. Okay, so now let's go back to this. So if x minus 2 is less than 1, then absolute value of x squared plus 2x plus 4 is less or equal to then the absolute value of x squared plus 2 times the absolute value of x plus 4. Well, what does that equal to? Well, we don't know what it equals to, but we certainly know that it's going to be less than what? Less than 3 squared plus 2 times 3 plus 4, which equals to 19. Why is it going to be less than 19? Well, because the absolute value of x is less than 3, the absolute value of x squared will be less than 3 squared, which is 9. Because the absolute value of x is less than 3, the absolute value of 2 times the absolute value of x will be less than 6. And finally, the 4 carries over. So, if x minus 2 is less than 1, x cubed minus 8 is less or equal to than, strictly less than 19 times x minus 2 absolute value. The 19 comes from this factor, and we already had factored this down to absolute value x minus 2 times absolute value of x squared plus 2x plus 4. Alrighty. Well, now this is less. So now suppose delta equals to the minimum of epsilon over 19 and 1. Then x cubed minus 8 is less than 19 times x minus 2, which is less than or equal to 19 times epsilon over 19, which is equal to epsilon. And we're done, because we've shown that, and x minus 2 is less than delta. So we've shown that if x minus 2 is less than delta, with delta defined this way, then x cubed minus 8 in absolute value will be less or equal to than epsilon. I'll leave this for a second up. I will look at I'll look at what's going on. If you have any questions that you yourself want to ask, make sure to ask in chat or use the form !ask if you have any more involved specific questions that you've looked at. Okay, so I think we took a screenshot. Let's do another quick recap. I'll just need to add the directory again, and let's check. Okay, this is the last problem we solved. The problem we solved was show that the limit of x cubed as x goes to 2 is 8. Aha! First, we're gonna answer that in a second. Just look at the recap, and you will see where the magic came from. So, we know that we have to do something with the x cubed minus 8. To do something with the x cubed minus 8, we factored it down to x minus 2, as you see in the middle of the board right now, times x squared plus 2x plus 4. Now, if x minus 2 was less than delta, we again, because we don't want to solve quadratic or cubic inequalities, we want to find some nice bounds. And for now, we're just going to assume that x minus 2 was less than 1. In other words, if delta was less or equal to than 1, then what can we say? Well, it turns out we can say quite a lot. As a matter of fact, the thing that's on the middle or in the bottom there of your screen, the absolute value of x cubed plus 2x plus 4 term would be bound above by 19. Why 19? We derive that on the next board. Because x minus 2 in absolute value was less than 1, then x would be less than 3 in absolute value. Why? Because for your absolute value to be less than 1, the number itself has to be between -1 and 1. And since x minus 2 was between -1 and 1, x itself has to be between 1 and 3. In other words, its absolute value cannot go above 3. And now, because the absolute value of x was less than 3, the absolute value of x squared plus 2x plus 4, after you apply the triangle inequality in the middle of that board, is less than or equal to 3 squared plus 2 times 3 plus 4, which equals to 19. That's where the 19 itself came from. And now remember, and I will just switch back to the previous slide, hopefully it's not too jarring for anyone. Remember that x cubed minus 8 in absolute value is less than or equal to x minus 2 in absolute value times absolute value x squared plus 2x plus 4. And we just said that if x minus 2 was less than 1, that second term, the quadratic term, was less than 19. So you get 19 times x minus 2 in absolute value is bigger than x cubed minus 8 in absolute value if x minus 2 was less or equal to 1 in absolute value. So far, so good. Now suppose that delta equal to the minimum of epsilon over 19 and 1. Well, then, if x minus 2 was less than delta, from what we just reasoned about, because delta is less than 1, absolute value of x cubed minus 8 would be less than 19 times x minus 2 in absolute value. This is because delta is less than 1. And now because delta is less than or equal to then epsilon over 19, you can just substitute epsilon over 19 for x minus 2 in absolute value. And that's where the epsilon over 19 comes from. You're just... I've skipped maybe one line in this entire proof, but again, as you're working through it, as you're trying to find that delta, it will be very clear why there's an epsilon over 19. It's because of that 19 that we derived a little bit further up on that board. Okay. This presentation dragged on for a little bit longer than I wanted it to. I just want to write down 2 more things about continuity and limits, and then if you have any questions, I will answer them. So let's write stuff up about continuity and limits. Limits and continuity, so limit laws. And you have the following theorem. We're not going to prove the theorem, but it's important to be able to at least recognize it. So theorem, suppose the limit as x goes to a of f of x equals to capital F and the limit as x goes to a of g of x equals to capital G, then part A, the limit as x goes to a of f of x plus g of x equals to f plus g, to the limit as x goes to a constant times f of x equals to a constant times capital F, that same constant, these are the same for any r, or for any c in r. The limit as x goes to a f of x g of x equals to f times g, and the last one is that the limit as x goes to a f of x over g of x equals to f that's not f divided by g if g is not 0. How you would use these? Parth, yes. If this is something you're interested in knowing about, and if you feel this is useful to you, then you should study it up. The lines of reasoning are very, very straightforward. But the limit laws, on the other hand, are very straightforward to apply. And the limit laws actually allow us to know that once we know one limit, to compute many, 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 many more limits. So let me just give you the intuition of what's going on here. The limit of the sum equals to the sum of the limit. If you multiply your function by a constant, it's as if you've multiplied its limit by that same constant. If you multiply two functions together, then it's as if you're multiplying their limits together. And if you take the quotient, then it's as if you've taken the quotient of the limits, but it only can happen if the limit of the denominator is not 0. Otherwise, you're in a little bit of trouble. We will learn how to resolve some of that trouble, but for now, we would just be in just a little bit of a pickle as to how the quotient stuff will work. Okay. So now I'm not gonna prove these. These are usually proven in a higher level math class, but we're going to use them, and we're going to use them to substitute for epsilon-delta proofs, because epsilon-delta proofs are long and boring. We really like not long and boring stuff in math. At least I do. So what will happen here is we will do exactly the same problem that we did before, but we will do it using the limit laws. So show that the limit as x goes to 2 of x cubed equals to 8. Solution: x cubed equals to x squared times x. And we know the limit of x goes to a, x equals to a, so the limit as x goes to 2 of x equals to 2, and the limit as x goes to a of x squared equals to a squared, so the limit as x goes to 2 of x squared equals to 4. And now use the limit laws to get that the limit of x cubed as x goes to 2 equals to 2 times 4 equals to 8. We're done. Voila. Look at how much shorter this was, right? So the epsilon-delta definition is extremely rigorous for a good reason. Without rigor, there's no math. For practical purposes, when you're computing limits, it often suffices to just use the limit laws and use what you already know about certain other limits than the one you're trying to compute. Okay. Here is a theorem that you can prove straight up using just the limit laws. The limit as x goes to a of x to the n equals to a to the n for every n greater or equal to 0 and a in the reals. N doesn't have to be an integer power. But for now, you can just think of it as an integer power. Alrighty. Let's take a screenshot. I don't think we need to do a quick recap of this. I'll just flip the board. Here are the limit laws. There's 4 of them that are worth knowing. Maybe the book lists one more. What happens when you multiply, add, and divide 2 functions is what the limit laws cover. And exactly what you want to happen happens. Under summation, you just add the limits. Under multiplication, you just multiply the limits. Under quotients, you just take the quotient of the limits. And that's about it for the rigorous definition of the limit. Just want to mention something quick about continuous functions, and then I will open the floor to any questions that you guys might have. Again, the form to ask is either !ask in chat, or just ask the question in chat, like Parth was already doing that. Let's check out how this will go. So continuous functions. And I use a lot of abbreviations. Cont is continuous. Functions are abbreviated to f-n, apostrophe s. Life is too short to spell it out completely. So definition. A function f is continuous at a if the limit as x goes to a, f of x equals to f of a. Such a nice, elegant little definition once we know what is going on here. Now, once you understand what is the statement is saying, a lot of possibilities open up. For example, what is this telling us? It is telling us that the closer we get to x in the argument, the closer the function gets to its own value at a. And the closer and closer and closer we get to a, closer and closer and closer, the closer f of x gets to f of a. And it turns out this is a critical property of functions. It is the property that allows us to do a lot of stuff. It's the property that would allow us to integrate functions. It's the property that eventually maybe would allow us to talk about derivatives a little bit more. And it's just a very nice property. Like, continuous functions are, in a way, the building blocks of what we're doing. So examples are the following sets of functions: polynomials, exponentials. And what's an exponential in my book? E to the 2x, e to the x, e to the x squared plus x. All of these types are, let's just keep it to e to the x, e to the 2x for now. Polynomials, what is a polynomial? X cubed plus x plus 1, x squared plus x, x, etc. Logarithms and trig functions, they're all continuous. So say L or log base 2 of x, or sine of x, cosine of x. It's worth noting that, say, the tangent has a discontinuity. It has quite a few discontinuities, but it is, it has quite a few points that are not even in its domain. But every point that is in its domain is a point of continuity. So definition: if limit x to a, f of x equals to a, f of a, then a is a point of continuity. Okay. So every point in the domain of these functions is every point in the domain of these functions is point of continuity. Number noise, tan x is discontinuous due to repeating. Yes, the tangent is discontinuous at some points because some points are just not in the domain, because at some points you're just dividing by 0. So by definition, at the points at which you're not defined, you are not continuous, right? It's not a point of continuity. Okay. Yes, you want to be continuous over the defined domain. Anything that's not in the domain you don't care about. But yes, you're right that the tangent has vertical asymptotes in some places. And that's nice. Okay, now what's the connection between 2.4 and 2.5? The connection between 2.4 and 2.5 is when you are trying to prove that something is a continuous function, you will have to use limits, and you will have to show that exactly this holds. Now, the functions that we could actually reasonably ever ask you to show are continuous at this level, I think you're okay, Price. The functions that we could actually reasonably ask you to show are continuous at this level are, let's just take the screenshot. Functions that we could ask you to show are continuous are just the polynomials, which is why I actually spent so much time today talking about these polynomials. Right. So, problem, show x cubed is continuous at 1. Solution, limit x goes to 1 of x cubed equals to 1 cubed equals to 1 equals to 1 cubed. And this is by limit laws or theorem or whatever you want to call it. And then 1 cubed is exactly the evaluation of x cubed at 1, so we're done. Right? So we went from writing about 3 boards to show that a certain limit equals to something else, to using the limit laws and a theorem about the powers of x to show that the limit equals to exactly the function evaluated at the point. Let's do another problem. Like, these are super quick. Show x, show x cubed plus x squared is continuous at 5. Solution, limit x goes to 5 of x cubed plus x squared equals to limit x goes to 5 x cubed plus limit x goes to 5, my handwriting is dying, x squared. This is by the summation limit law. And now by the power limit law that we wrote down, by the power theorem, you know that the limit is x goes to 5 of x cubed is 5 cubed. So this is 125 plus 25, which equals to 150, which does equal to 5 cubed plus 5 squared. Then you're done. These seem like tautologies because they are, once you understand enough about the problems. Once you know enough, all of these are just tautologies. All of these you will just breeze past. Okay? Now, let's look at one more. I hope you do not have any questions about this. If you do, we will capture them in a second. My screenshot didn't go through. Now it did. Okay. Let's do a hard one. Let's do one that involves quotients. And it's not just a continuous function problem, but it is the following problem. So show that x squared plus x, show that if f of x equals to x squared plus x minus 2 divided by x minus 2 if x is different than 2, and let me just do the math, 3 if x equals to 2, show that this function is continuous. F is continuous. So this is the problem that we're trying to solve. We're defining a function that is x squared plus x minus 2 divided by x minus 2 if x is different than 2, and it's 3 if x equals to 2. We want to show that this function is continuous. Well, let's do it the following way. So proof or solution. If a is not 2, let's just show that f is continuous at 2. Right? The rest you can try to do at home, but let's just show that 2 is a point of continuity. Okay, so what's going on here? Well, f of a, or excuse me, f of 2 equals to 3. So we want to show, WTS, want to show that limit x goes to 2, f of x equals to 3. Okay. Well, how are we going to do that? We're going to be somewhat smart. Look at if x is not 2, f of x equals to x squared plus x minus 2 divided by x minus 2. The reason we cannot use the quotient rule to immediately say what the limit of this function is as x goes to 2 is because we would be dividing by 2, and we don't want to do that. I also do not allow you to use L'Hopital's rule yet, and if you don't know what L'Hopital's rule is, we will learn that very soon. What we do know, however, is how to factor quadratic stuff. X squared plus x minus 2 is 0 at 1. And oof, did I mess this up? I did mess this up. Let's make it a minus. See, that's the risks of making up stuff on the spot. This should work now. X squared minus x minus 2 divided by x minus 2. So what are the zeros of the numerator? They are 2 and negative 1. Correct? So the top factors as x minus 2 times x plus 1 divided by x minus 2. This in turn equals to x plus 1. So if x is not 2, f of x equals to x plus 1. So f of x equals to x plus 1 if x is different than 2, and 3 if x equals to 2. Hold up, x plus 1 is 3 when x equals to 2. So f of x is just x plus 2. X plus 1. So this function is a very well hidden copy of the function x plus 1. Yes, it would be annoying to use because of the quotient. Yes, I agree with this. So our f of x is x plus 1 in disguise. And now it's up to you to show, so exercise y is x plus 1 continuous at 2. It's one line. Hopefully you can work it out. Okay. I'll give you a final definition and then I'll answer any questions you guys have. So take a screenshot and move back on. So final definition. A function f is continuous on the set D f for every x in D. F is, or x is a point of continuity of f. So f is continuous on D if for every x in D, x is a point of continuity. So when we say a function is continuous, we usually mean that it's continuous on its domain. Okay. So we have the notion of continuous at a point and continuous on a set. And they're very closely related. They're almost the same thing. Continuous on a set means you're just continuous on every point in your domain. Or on every point in that set. So I've spoken for an hour. Hopefully you had gotten to the point to read about these things. And if you haven't, that's fine. You can ask questions about the previous sections of the book. And I will answer those. But now is your turn to ask any questions, anything about what we did today. And I am open to answer them. So either use the form. Again, it's not a Twitch command, ask. Use the form if you have a longer question, and if you have a short question, just type it out in Twitch chat and I will read it. And I will just relax for a second, have a sip of water. I should probably also make a Discord command. Maybe later. So we do have a Discord. How about this? If you're watching this and you're not currently in our Discord, just whisper me on Twitch. Tell me a little bit about why you would want to be in a math Discord about calculus. So this is specific about calculus. And then if you're serious about learning this, I will probably just add you to the Discord. But yeah, if I don't get a question in about 5 minutes, I will just end the stream and go have dinner. Again, there's a lot of self-studying. I will post the homework and the quiz tonight, so you can test your knowledge. And then I will also post what you should be doing for next week. But yeah, I'm here for you for the next about 5. Explain how to prove that in exercise 2.3.65. Again, let me just look. 2.3.65. 2.4, 2.3. So let's just see how I would do this. Is there a number A such that... Okay, so let's look at this problem. I'll just copy it on the board. So, is there a number A such that the limit x to 2 3x squared plus ax plus a plus 3 divided by x squared plus x minus 2 exists? Okay, I mean, let's just think about this for a second. The quiz will be on the sections 2.4 and 2.5, same as the homework. Okay, so let's just read this question. So, is there a number A such that this limit exists? And if it exists, what is its value? So this is a 3. Let's look at the denominator. Like, why can't we just plug in 2 and say that the top over the bottom is the limit? Because the limit of the bottom is 0 as x goes to 2, right? So this thing goes to 0. Well, for that thing to go to 0 and for us to still be able to have an existing limit, we would have to make the top go to 0 as well. And when does a polynomial go to 0 at a certain point? Well, it goes to 0 when it evaluates to 0 at that point. So the hint here is that 3x squared plus ax plus a plus 3 should be equal to 0 if x equals to 2. right? So that you can get the cancellation that we previously got in the example that we just did. Let me see if it's still on the back of the bird. Right here, we could factor the top as x minus 2 times x plus 1. When we divided it by something that went to 0, right, there would be a problem. Alrighty. So what is 3x squared plus ax plus a plus 3 evaluated at 2? It is 3 times 2 squared plus 2 a plus 3. And this equals to 15 plus 3a. And this has to equal to 0. So a equals to -5. And let's see what happens when a equals to -5. You get limit x goes to 2. 3 times x squared minus 5x minus 2 divided by x squared plus x minus 2. Did I mess this up again? It should be -2, no? Yeah, okay, this is a -2. And I messed this up. Let's fix it. There's no shame in messing things up. Start over. We want 3x squared plus ax plus a plus 3 to equal to 0 if x equals to -2. So plug in -2, you get 3 times -2 squared plus a times -2 plus a plus 3. This should equal to 0. So you get still 12 minus 2a plus a plus 3 equals to 0. So 15 minus a equals to 0. So a equals to 15. Okay, so let's look at it again. So you get 3x squared plus 15x plus 18 divided by x squared plus x minus 2. Right, so let's just verify that -2 is still a root. 12 plus 18 minus 30 is 0. So -2 is a root. Let's figure out what the other root is. Well, we can be a little bit smarter about this. 3 times x squared plus 5x plus 6 over x plus 2 times x minus 1. And now the top factors as 3 times x plus 3 times x plus 2 divided by x plus 2 times x plus 1. So the x plus 2's cancel out. So if f of x, or excuse me, if x is not -2, then f of x is 3 times x plus 3 over x plus 1. And now you can just use the quotient rule on this. So let's take a screenshot. I hope you can see what I'm doing. You can, okay. How to prove quotient limit law is one-sided, not a criteria. Okay, I understand what you're saying. How do we show that there's only one value that works? This is the only value for which the question is not asking you to show that there's only one value, right? So you're not at the stage. You're not at the stage in which you can conclude there's only one value. We will be able to conclude there's only one value in about a week. But unfortunately, right now you cannot conclude there's only one value. And the question does not ask you if there's only one value. The question asks you if there is a value for which this holds true. There is. Now, to see that there would only be one value, at this stage, you would have to just work out that if a is different than 15, then the limit would not exist. And you could technically do that. I would not recommend. Right, we will learn how to do this in about a week. Then you would be more than able to do. Okay. Any other questions, my friends? I hope this satisfies your curiosity. You probably found that a equals to 15 works. There is a good reason that no other a works. but we're not ready to know it yet. I am not live on Mixer, but let me see if I can fix that real quick. Timers. Disable. Okay, it will stop telling me that I'm live on Mixer. I used to do this on Mixer, and then I realized that, you know what, like, nobody goes on Mixer anyway. So I might as well just do this on Twitch. And I also will never say Twitch chat in Mixer ever again, which was always very confusing. But yeah, so tonight I will post the homework. The homework will be similar to the questions we solved today. And then there will be a short quiz. And I'm still trying to figure out if I actually want you to use paper for the quiz or use Google Forms. But yeah, 2 more minutes for any final questions. This first week is a little bit slow. And it's slow because there's a lot of prerequisite material, so to speak, to get through in the first 2 chapters. But now we will slow down. Like, we will not cover like a chapter and a half in 1 week. We will slow down and we will just focus on covering maybe about a chapter per week. With including a lot of, maybe half a chapter, sometimes maybe a full chapter. I was sick this week and I didn't read the book. 2.4, let me just look at it. So if you just look at the questions after 2.4, questions 19 to 32, prove the statement using the epsilon-delta definition of a limit, and then you have 14 problems, some of which we already solved. So the TLDR is the epsilon-delta stuff is important if you want to study mathematics. And it's important to understand how that works. It is also usually the most annoying question on an exam. So if you're trying to prepare for an exam in calculus at any point in your life, and we're talking about calculus 1 in particular, you will usually have a very annoying, very like straightforward yet challenging if you don't know what you're doing question about epsilon delta. They're not that hard. They're very methodical in the application of the process. You just need to look back at what we did today, especially that problem we solved for the limit of x cubed equal to 8 as x goes to 2. That is your best guideline for how to approach these problems. You have to use the triangle inequality, and you have to define the delta as the minimum of 2 values. And then, once you understand that problem super well, you just crack everything else open, and you start understanding the entire topic. I hope that makes sense. Again, like, I know this is daunting, and I know that maybe for some of you, especially if you're studying for the AP, I do not remember if on the AP AB the epsilon delta definition is kosher, testable, whatever you want to call it. But if you're trying to prepare for college, like, epsilon delta is your bread and butter for like at least 20% of your first exam and maybe another 20% of your final, because there's nothing else to ask. You can only ask people to do so many derivatives, and you can only ask people to do so many like basic integrals or optimization questions. But this is by far the most conceptual part of the book, like, and it's in chapter 2. AP does not it. Okay. That's fine. So if you're studying for the AP, just learn how to compute limits using the limit laws. But if you want to know more, if you want to practice, if you want to learn, then we're not studying for the exam, we're studying for actually knowing. Or at least I would like you to do that. Anyway, so I saw a couple of you here. Final questions, final chance for questions. We've been live for almost an hour and a half. I'll take any questions, otherwise I will just post the vote on Discord and go hang out. Thank you everybody for following. If you followed, if you didn't follow, make sure to drop a follow. RFCZZZ followed me a bunch of times. I appreciate it, my friend. But yeah, if you have no further questions, then final chance. Khan Academy has 4 videos on it, but they're confusing. Yes, so just to elaborate why I'm doing this when Khan Academy exists and when OpenCourseWare exists. It is because very rarely do you get the opportunity to interact with somebody live as they're doing math. And it's very important to have, it's almost like performance art. Like, it's very easy for you to lose track of something as somebody is doing it in a video, right? And maybe it's even easier to lose track when somebody is doing it live. But I think it's very important to have this back and forth that's possible. If you don't understand something on Khan Academy, you have to go to Stack Exchange and ask. But if you don't understand something as I am doing it, then you can ask a question in Twitch chat. Then I can clarify. It's almost like being in the lecture hall together, except, you know, we're not. We are miles apart, but we can still do this because of this wonderful thing called the internet and live streaming. So, if there are any more questions, once I post the homework, once I post the quiz, feel free to ask them in the Discord. Nobody used the form, and that's fine. Maybe it's because, you know, it looks like a Twitch command. But it's not. It's a Twitch command, but it links to a form. If you have any questions, you can also ask them in the forum. I will go dark for now. This part of the stream is done. If you get a notification that I'm going live again, it's for a different part of math that you probably don't want to study right now. But if you want to just listen to how linear algebra works, then you are more than welcome to do so. For now, I bid you good night and good luck.